We now have an understanding of the structure of the IP packet and its associated addressing schemes. In the next section of this training module, we will investigate how IP can be used to transmit information between computers. We will look at the various methods a computer can use to obtain an IP address, and then how it uses this address to transmit information over a wide area network constructed of routers. We will pay particular attention to the processes routers use to build and maintain the routing tables necessary to correctly deliver an IP packet from one computer to another over networks that can span the world. On TCP IP networks, the ARP protocol is used to match up an IP address with a Media Access Control, or MAC, address. An IP address is a high-level inter-network address that identifies a specific computer on a subnetwork of interconnected networks. A MAC address is the hardwired address of a network interface card, or NIC. MAC addresses are only used to forward frames between computers attached to the same network. They cannot be used to send frames to computers on other networks that are interconnected by routers. IP addressing must be used to forward frames across router boundaries, assuming TCP IP networks. ARP is used in all cases where one node on a TCP IP network needs to know the MAC address of another node on the same network or on an internetwork. Basically, ARP lets a computer ask the question, will a computer with the IP address w.x.y.z send me its MAC address? This ARP message is broadcast on the local network, so all nodes hear it, but only the node that has the IP address in question responds. Router AB and router BC connect three subnetworks, A, B, and C. Hosts A1 and A2 are on network A, and host C1 is on network C. Subnet B is an interconnecting LAN or a WAN. Assume host A1 wants to transmit to host A2. It knows the IP address of host 2, but must have a hardware address to transmit on the network. To get the address, it creates an ARP request and broadcasts the frame on the network. All the other hosts on the network receive the broadcast, but only host A2, which owns the address in question, prepares an ARP response that contains its MAC address and sends it directly back to host A1. Host A1, for future use, saves the response in a cache. If host A wants to transmit to host C1, router AB must get involved. ARP is used to discover the MAC address of router AB, and all frames for transmission to host C1 are then sent to router AB's MAC address. Router AB then forwards packets to router BC. Presumably, router BC already used ARP to determine the MAC address of host C1. It simply forwards the packets in frames addressed to host C1 on the network. We will explain a little later how the routers AB and BC know about how to communicate across subnet B. To make ARP efficient, each computer caches IP to MAC address mappings to eliminate repetitive ARP broadcast requests. Most operating systems age ARP entries in the cache if they are not used for some time. Entries are made to the ARP cache on a first response basis. When a computer is first started, a bootstrapping routine on ROM provides it with enough logic to obtain startup programs from a permanent storage device, which includes the IP address of the machine. As an administrator, it's great to have a little list. A list of PCs and IP addresses used, a kind of a master directory of which IP addresses have been used so far. Obviously, you'd have to consult it when putting TCP IP on each computer. Enter Murphy's Law. It's unfortunate that you just never seem to have that list handy when you need it. One way to deal with this is to start keeping this list of computers and IP addresses on one of your servers in a common hosts file. This serves two purposes. Firstly, it tells you which addresses are already used, and second, it gives you a hosts file for the local computer's hard disk. However, that's kind of a hassle too. Why on earth should we have to manually tend to what is clearly a rote, mechanical, the kind of job that computers are good at. If the computer is a diskless workstation, a computer with no local storage device, then network loading of boot information must be obtained from a network server. The diskless workstation has a special ROM inserted on its NIC, network interface card, that directs it to contact a specific computer on the network. This computer then has a program that sends a startup disk image to the diskless workstation so that it can boot. All subsequent disk access is performed on network servers. Network computers need quite a bit of information to get started, including a network address and the location of important services. In the TCP IP environment, a system needs an IP address, a default router address, a subnet mask, a DNS, domain name system, server address, and some other parameters, depending on the environment. However, creating a startup configuration file for every diskless workstation on a network can be a daunting task, especially if the information changes often, as it might for mobile users. A number of protocols have been developed to dynamically assign their IP addresses, as will be discussed in a moment. TCP IP also includes a protocol, Reverse Address Resolution Protocol, RARP, that allows one host to obtain an IP address from another host. When a diskless TCP IP workstation is booted on a network, it broadcasts a RARP request packet on the local network. This address packet is broadcast on the network for all to receive because the workstation does not know the IP address of the server that can supply it with an address. It includes its own physical network address, the MAC address, in the request, so the server will know where to return a reply. The server that receives the request looks in a table and matches the MAC address with an IP address, then returns the IP address to the diskless workstation. RARP was a good first step, but had a number of limitations. It was not very helpful, and was difficult to expand to a general dynamic IP allocation system for both diskless and networked workstations. BootP is an Internet protocol that can provide network configuration information to diskless workstations or other workstations, if necessary, on a local network. It works in a similar manner to RARP. Information returned by the BootP server to the booting computer includes its IP address, the IP address of the server, the host name of the server, and the IP address of a default router. It also specifies the location of a boot image that the booting computer can obtain in order to complete its startup operation. The administrator still assigns an IP address to each MAC address. This was a great improvement over the static IP addressing system we've described so far, but the administrator still needs to ensure that every MAC address has a unique IP address. Dynamic Host Configuration Protocol, DHCP, as the name suggests, is designed to help reduce configuration time for TCP/IP networks by automatically assigning IP addresses to clients when they log on. DHCP centralizes IP address management on central computers that run the DHCP server program. At least one DHCP server must exist on a network. Once the DHCP server software is installed, you create a DHCP scope, which is a pool of IP addresses that the server manages. When clients log on, they request an IP address from the server, and the server provides an IP address from its pool of available addresses. DHCP is a boon to network administrators. It relieves configuration problems that are inherent with manual or one-to-one relationship configurations. Like BootP and most of the other TCP/IP services, DHCP uses a client-server model. There are three basic types of DHCP devices. First, there's the client, or the software, which resides in a host and requests an address assignment using DHCP. Second, there's the server, which provides DHCP services and administrative tools. Finally, there is a DHCP relay agent functionality that is typically offered by a router. With a relay agent, the routers are configured with the address of the DHCP servers, obviating the need for a DHCP server on every IP subnet. DHCP defines three address allocation mechanisms. With automatic allocation, the server assigns a permanent IP address to a host. In dynamic allocation, the server assigns an IP address to a host on a temporary basis. The host can keep this IP address for some period of time, called the lease, or until it explicitly releases the address. Finally, with manual allocation, a host's IP address is assigned by a network administrator, and the DHCP server is used simply to convey this address to the host. Dynamic address allocation allows automatic reuse of IP addresses. It is ideally suited to networks with many roaming systems. A laptop, for example, can be assigned an IP address from one location of the corporation's address space on one day and receive an IP address from another location's address space on the next day. Alternatively, it may be used by an internet service provider that has more subscribers than dial-up ports. Rather than assign every customer an IP address, assign a pool of addresses to the modem pool and assign addresses dynamically when customers dial in. Domain naming and its most visible component, the Domain Name System, or DNS, is critical to the operation of the Internet. The average European phone number, with area code, is 9 or 10 digits in length and encodes 10 to the power 10, or 10 billion possibilities. The Internet IP address, at 32 bits, encodes 2 to the power 32, or 4.2 billion possibilities. For humans, it is impossible to remember all these combinations, so how can we build an effective directory of these difficult large numbers? The telephone company solves this problem with lots of large paper directories and operators you can call and ask about numbers not in your directory. Internet solves this problem with a hierarchy of simple mnemonic names called domain names. Instead of remembering 205.216.138.22, all I need to know is the host's domain name, sirius-uk.com. Some people think the dots in a domain name correspond to the dots in the numeric address. This is not the case. There are always 3 dots in an IP address, separating its 4 constituent bytes. There are a variable number of dots in a domain name. The naming system is hierarchical in structure. The tree has a topmost root level and major divisions called domains branch from the root. In the diagram, not all domains are shown, specifically those for other countries, such as .co.uk or .fr. Only the top-level domains are listed here. An ISP is probably part of the .net domain, while a company is probably part of the .com or local national domain. In February 1997, the IAB announced 7 new generic top-level domains, GTLDs, in addition to the existing ones, .com, .net, and .org. The new fields are .firm, for businesses or firms, .store, retail, .arts, culture and entertainment, .rec, recreational entertainment, .info, information services, and .nom, individuals or personal nomenclature. With the DNS, the capability is in place so that a host can learn another host's IP address from its name, or vice versa. Consider that when a user wishes to connect to a given site, such as www.sirius-uk.com, the application must send out a request to the local name server to find out that this host's IP address is 205.216.138.22. In fact, the scenario is usually a bit more complicated than a simple query response. When an application needs to learn the address of some host system, it sends an appropriate message to the local name server. If the requested name is not known by the local name server, it is the local name server's responsibility to forward the request to other name servers until the request is satisfied. Only when the name has been translated to an address can the local host try to determine a route to the destination host. There are a number of TCP/IP utilities that can be used to examine DNS records. The most common is NS Lookup, or host. commonly available on Unix systems and other commercial TCP IP packages. A bridge is a LAN connection device with two or more ports that forwards frames from one LAN segment to another. The bridge can also offer connectivity between remote sites. Any elements connecting to one side of a bridge form a completely separate network to the elements connected to the other side of the bridge. The bridge, by nature of its operation, creates multiple logical networks. Any traffic transmitted on one side of the bridge will propagate to devices connected to that network. The traffic will arrive at the bridge as it is considered part of the LAN. Bridges operate at the lowest layers of the 7-layer architecture stack. They understand the media access control frame and its header fields that are found in both Ethernet and token ring LANs. This is a Layer 2 data link protocol. They have no understanding of TCP IP layers. Routing is the act of moving information across an internetwork from source to destination. This process may involve the information flowing across a number of discrete networks, often called subnetworks. These may be owned and operated by different organizations, as is the case with the Internet. To complete this task, the router undertakes a number of tasks. Firstly, the router receives data on one interface. The router then looks at the destination address of the data packet supplied in the network layer header. It then performs a lookup in a table called the routing table, which tells the router which interface to use next. Finally, it sends the data packet out on the chosen port to continue its journey to the remote machine. The router operates at layer 3 of the 7-layer architecture stack and utilizes the information found in the network layer to provide its services. As already stated, IP is the most common layer 3 protocol in use in networks today. The router offers interconnection between LANs where a suitable route is selected, rather than simply making a forwarding decision. The router therefore offers great advantage in functionality, but requires more processing power than a bridge. To successfully route a packet through the internetwork, a router must determine the packet's path. Let us look at an example of how a routing network achieves this. Assuming that device 6 of network 1 wishes to pass data to device 4 of network 3, device 6 will generate an IP datagram. The datagram will be placed on the LAN in MAC frames. These will be addressed to the local router. The router will then examine the destination IP address of the IP datagram to determine which path the datagram should take. As shown, its routing table instructs the router to pass the datagram out on port 2, encapsulated in whatever wide area network WAN protocol is used. Routers can support complex network architectures. In this example, the router has two different WAN links to choose from. In real networks, the choice is likely to be even more complex. From an economics point of view, a bridge tends to operate between LAN segments on a point-to-point link basis. Routers tend to interconnect fully meshed networks and provide features to maximize the efficient utilization of expensive WAN facilities. On arrival at the router local to network 3, that router will examine the destination IP address and determine that the destination device is a local machine. The router will send the datagram out on its local port, where it arrives at device 4. The datagram will be encapsulated in the appropriate LAN frame for the LAN technology of network 3. Hence, the LANs on either side of a routed network do not need to be the same type as they do in a bridge network. For example, the device 6 may be attached via a token ring LAN, whilst device 4 may be connected via an Ethernet LAN. The routing process used by IP is relatively straightforward. However, there are a few issues yet to be cleared up. For one thing, nothing has been said about maintaining the routing tables. As shown, IP, like any network layer protocol, is simply consulting the routing table. So how tables are created and maintained is very important to the success of IP networks. This is the task of the routing protocol. Early routing protocols were static. The routing tables were manually created and maintained. Obviously, this approach is somewhat inflexible and is not tremendously responsive to changes in the network. There is one thing you can always say about networks: they will change, grow, and fail. Dynamic routing protocols automatically adjust to reflect changes in the network. While IP itself does not define the specific routing protocol that is to be used, the routing protocols used in TCP/IP are typically dynamic. Furthermore, they are distributed. This is to say, each device makes its routing decisions independently. We've already seen that there is really no explicit route a packet is given to follow. Rather, each router decides how best to reach a given destination. Through the collective action of the routers, a datagram is directed towards its destination. In the IP environment, we will also find that the devices are in some way cooperating to exchange information necessary for making intelligent routing decisions. Therefore, the role of a distributed routing protocol is twofold. Firstly, it must define a mechanism for selecting the best path, or at least one that is in some way measurably better than other options. A routing protocol must also define a mechanism by which any device that must make routing decisions can receive the information necessary to make those decisions intelligently. Notice that this means the routing protocol is not only updating the routing table, but may be extracting information from it to send to other routers and hosts in the internetwork so that they can update their own routing tables. There are two predominant standard routing protocols used in TCP/IP environments. They are the Routing Information Protocol, RIP, and the Open Shortest Path First, OSPF. A third routing protocol, Border Gateway Protocol, BGP, is used extensively within the Internet and is therefore very important to the Internet service provider industry. We will examine each of these in turn during the next couple of slides. In a distance vector routing protocol, neighbors exchange vectors that reflect the distance and direction to a specific subnetwork. For example, router A has just sent a set of 4 vectors to router D. By doing so, it has informed router D that router A is 2 hops or links away from subnet 1, 3 hops away from subnet 2, 2 hops away from subnet 3, and directly connected to subnet 4. Router D can now learn how far it is away from these subnets if it routes via router A merely by incrementing each cost entry in router A's table by 1. If router D receives a similar set of vectors from each of its neighbors, it can use the information to build a full routing table. The routing table will contain each of the network addresses reported by D's neighbors, as well as the addresses of the subnetworks to which D is directly connected. Associated with each subnetwork will be the distance to that network and the IP address of the router that lies along the path. In this example, router D has selected router A as the best next hop route to subnet 4 because A reports a path of 1 hop, while router C is reporting 3 hops. In a similar fashion, D has made decisions about routes to subnet 1 and subnet 2. Because router D is directly connected to subnet 3, no other path is likely to be better. Router neighbors do not have to be synchronized for datagrams to be routed. Typically, each router is simply required to send the vectors periodically, usually every 30 to 90 seconds. The receiving router simply compares the vectors to the current values it has for those subnetworks and updates the routing tables to reflect any better routes it has learnt. Distance vector routing protocols can simply extract the vectors to be sent to the neighboring routers from the routing tables it is maintaining. Note that the entire table is usually not sent. Only the subnet address and the cost are transmitted to neighbor routers. It is not necessary for a distance vector protocol to limit itself only to hop count as a metric. In fact, there are a number of distance vector protocols that use metrics such as delay or even complex composite metrics, as in the case with Cisco's Interior Gateway Routing Protocol, known as IGRP. The Routing Information Protocol, RIP, is a distance vector protocol defined for the Internet as part of the TCP IP protocol suite. RIP uses hop count as its sole routing metric. Per the specification, a router extracts subnetwork and distance information from routing tables and broadcasts it to all neighboring routers and hosts every 30 seconds. RIP has a number of advantages. First, it is an exceedingly simple protocol to implement. Simplicity usually means it's inexpensive to develop and has low computational overheads. RIP has the added advantage of being widely implemented and supported. Historically, RIP has been the most popular routing protocol for use in TCP IP networks, largely due to its incorporation in Unix 4.2. Few router manufacturers have not implemented RIP in their products. Despite these advantages, RIP suffers from a number of serious shortcomings. RIP was designed for simple networks, and as networks have grown, the cracks in RIP have begun to show. Use of hop count as a routing metric is not always the greatest idea. In internetworks with links of varying bandwidth, hop count ignores the difference. RIP would prefer a 2-hops path over 64 kilobits per second facilities rather than a 3-hop path over 2 megabits per second facilities. To overcome this drawback, some network managers allocate high hop counts to low-speed links, but this can expose other limitations in RIP. Table exchanges, especially in large networks, can consume significant bandwidth. This is because the routing tables grow as the internetwork grows, and the exchanges between neighbors consist of a significant portion of the routing table. RIP also has a problem with convergence. A network only converges when all devices are routing based on common information. In a large network, it may take many router table updates before routers at the edge of a network are updated with any changes. To make convergence faster requires more updates. This consumes more network bandwidth. RIP compromises between the need to have fast convergence and the cost of bandwidth by limiting the length of paths to 15 hops, thus limiting table sizes. Finally, RIP's use of hop count as the only metric makes it virtually impossible to support type of service (TOS) routing. RIP2 was designed to address some of the inherent limitations of RIP1 while preserving its basic features. The basic message format remains the same. RIP2 makes use of unused fields in RIP1 to add support for password authentication of router table updates and to provide a 16-bit root tag that can identify individual or imported routes. RIP2 can also carry a 32-bit subnet mask field. As with the term distance vector, the term link state says a lot about how these types of routing protocols operate. Instead of vectors to calculate best routes, a link state protocol uses a database of link state information. The database contains information on the state of each link in the network and the routers that connect to them. This means that each router in a link state routed network must have a mechanism for discovering its neighbors and learning their IP address. Discovering neighbors is usually accomplished with special hello messages that include the name of the transmitter and information concerning the link. Once the router knows about its neighbors, it must create a link state packet, or LSP, containing the names of each of its neighbors and the cost of the link between itself and each of its neighbors, and then transmit its LSP to each of its neighbors. The LSP could contain information about the link's bandwidth, the current load, the cost, in real money, of using the link, and the current delay experienced across the link. Once it has received an LSP, a link state router must be able to store the information. This stored information is commonly referred to as the link state database. Using the information in the database, the router must calculate the shortest path from itself to any subnetwork in the internetwork. Using a formula, the router calculates a cost for each of its links. This formula may be based on different network criteria, such as available bandwidth or end-to-end delay. If a router has costs for all links in the network, it has sufficient information to calculate the shortest path from itself to any subnet in the internetwork. These costs would optimize paths based on available bandwidth, i.e. throughput. With a different formula, another routing table could be calculated that optimizes on delay, link cost in money, or any number of metrics. Open Shortest Path First, or OSPF, is a link state routing protocol. The IETF developed it for use in the Internet and is part of the Internet Protocol Suite. OSPF supports important functions not supported by RIP. As with all link state protocols, OSPF exchanges internetwork topology information by flooding small link state advertisements throughout the internetwork. The information is stored at each router in a link state database. Flooding ensures that all routers have exactly the same link state database. The information in the database includes addresses of all known routers, information concerning all known links and their associated costs, and the addresses of all known networks. Using the information in the link state database and Dijkstra's algorithm, the OSPF router calculates a minimum cost spanning tree with itself as the root. Using the spanning tree, the router generates a routing table for use by the Internet Protocol. If several metrics are defined for links in the network, some of the routers, or perhaps all, will be able to calculate differing routes based on type of service TOS parameters. This is a far better and more flexible system than the basic hop count mechanism used in RIP. Because OSPF places no upper bound on the size of an internetwork, it is possible to deploy rather large internetworks using this routing protocol. While it is true that OSPF tends to use less bandwidth than the RIP due to the small size of the messages transmitted, the amount of bandwidth can become appreciable as the network increases in size. OSPF defines a mechanism by which the routing updates can be authenticated. Only an authorized router can generate a routing update that will affect a change in other routers. OSPF supports the use of the type of service TOS field in the IP packet header. By allowing the definition of different TOS metrics for each link on each interconnection device, tables can be built with multiple entries, one for each TOS. OSPF does have some disadvantages. The protocol is more complex than RIP. As networks grow large, the link state database can become huge. This has two negative effects. First, it consumes more and more memory space. Second, it makes the process of generating a routing table more processor intensive. It simply takes longer to calculate link costs for more links, calculate the spanning tree for a larger network, and generate the large routing tables required by large networks. OSPF was developed from the OSI Intermediate System ISIS link state routing protocol. This is used in a number of ISP networks in place of OSPF because early implementations of OSPF on Cisco routers was unreliable. New versions of Cisco OSPF are better, but ISIS has often remained for historic reasons. OSPF uses the term autonomous system, or AS, to describe any collection of networks and routers under a common network administration. Although this seems a loose definition, recall that OSPF was developed for the Internet, where an AS distinguishes a private network from the public backbone. It is generally true that an AS uses a single routing protocol. To address this problem of increased processing and database requirements in large networks, OSPF introduces the concept of areas. An area is defined as a group of OSPF routers that exchange topology information. This means that a link state advertisement is flooded only to those routers that are part of the same area. Clearly, if the AS has only a single area, all of the routers in the AS will see the advertisements. However, if the AS is divided into several areas, the total amount of flooded traffic and the size of the link state databases can be significantly reduced. In effect, the larger network acts as though it were a collection of smaller networks. Because of the flooding limitation, the topology of one area is completely hidden from the routers in another area. This means that a router knows nothing of the network topology outside its own area. and routers outside of a given area see the area as a black hole. The networks are known universally, but the routers do not see the routers in other areas in a given area. Each area has a unique link state database, and all of the routers in an area should have identical databases. The Internet is the largest router-based network in the world. It is, in fact, not one network, but a collection of autonomous systems which are interconnected. We cannot achieve this connectivity using a simple flat routing system, hence the need to introduce routing protocol hierarchies. Inside an autonomous system, we use interior gateway protocols such as OSPF or RIP. To interconnect these autonomous systems, we use other routing protocols called exterior or border gateway protocols, known as BGPs. These can be found on boundary routers that connect the autonomous systems. These protocols allow dynamic table exchange between autonomous systems, allowing route filtering and route policies to be applied to limit the level of route advertisement. IGPs and BGPs allow a hierarchy of routers to be compiled in order that all routers have their route table size kept as small as possible. In many ways, the Border Gateway Protocol, BGP, is simply another routing protocol, yet it plays a very different role to the routing protocols we've discussed. BGP is the glue that makes the Internet work. The Internet is a large, complex collection of subnets, interconnected to form a global network. The subnets are owned and managed by different, often competing organizations. They are autonomous systems. An AS, while not truly autonomous, is autonomous in that it is administered by a single authority. BGP is the protocol used to forge the agreements on how these ASs pass information. In situations where there are multiple gateways within an AS, BGP is used internally between the gateways to determine which gateway offers the best route to a given destination network. Most routing protocols receive routing information, use it to build and maintain a routing table, and share that table, or a subset of the table, with other routers in the network. The information included in the routing table and shared with others on the network is usually controllable only by the physical configuration of the network and by the application of relatively manual filters to the ports of the router. What makes BGP unique is its ability to apply policies to the information contained in routing updates rather than the ports, and therefore accept or reject update information based on attributes of the information itself. Policy-based routing adds an interesting twist to the routing process. Conventional routing protocols make decisions based on the network and on some defined metric. Policy-based routing adds another level of consideration. The network administrator defines policies. They are usually driven by political, security, or economic factors. When routing updates are first received at a BGP router, they are subject to a series of policies, called input policies, that govern how or when the information will be stored and acted upon by the router. For example, a router may have a policy stating that it does not ever wish to access network 165.113.0.0 through AS2159. Thus, if an update contains network reachability information stating a path to 165.113.0.0 through AS2159, the router's input policy engine would prohibit that update from reaching the routing table, resulting in the router never using that path. Alternatively, an administrator might wish to label a path undesirable but not unusable. In that instance, the input policy engine could be set to add the router's own AS number to the path several times upon receipt, making the destination seem farther away and therefore less desirable to the routing process via that path. BGP allows for output policies as well. These can alter outbound routing advertisements, e.g., don't send any information about 165.113.0.0 to BGP peer 47, or change attributes in the updates based on policy information set by the network administration. So how do all these processes fit together to allow computers to communicate using TCP/IP? Let us consider a network for Company A. This network has 4 sites interconnected with routers using TCP/IP. It also has a connection to the Internet. The network operating system of Company A is Lotus Dominoes. As a normal background task, the routers have exchanged routing information. They are using RIP, so router A has constructed a routing table using distance metrics for the 4 subnetworks in the Company A network. A user plugs in this laptop onto the LAN in Site A. As the company uses DHCP, the computer requests a dynamic allocation of an IP address. This is achieved via the DHCP server located on the company LAN. Remember, all the time the routers and hosts are issuing ARPs onto the local LANs whenever they wish to send information destined for an IP address that they have no knowledge of. The responses to the ARPs will allow the routes and hosts to build caches of IP to MAC addresses for all attached devices. Now, at some point during the day, the laptop user wishes to obtain information from the sales server. All he has is the Domino's domain name of the device. He therefore has to request of the internal directory server the IP address for the sales server. The server provides him with the IP address 205.128.23.3. The user's laptop TCP/IP will generate an ARP broadcast requesting the MAC address of device 205.128.23.3. As the device is not local, the router will reply, telling the computer to send it to his MAC address. The user's application then creates IP datagrams with the destination IP address 205.128.23.3 and encapsulate them in MAC frames with the router A MAC address. The router will look up the destination IP address in its routing table and forward the IP packets to router D via router B. On receipt of the IP packets at router D, the router will encapsulate the packets in MAC frames with the MAC address of the sales server. Now the user wishes to browse the website of Company B. He makes a request for the IP address of www.companyb.com of the Domino's server. The server knows that this is not on the corporate network. After ensuring that the user has security access to the Internet, the Domino's directory server requests the IP address of www.companyb.com of the DNS server of Company A's ISP. This server returns the IP address 186.78.25.13 to the Domino's server, who passes the address back to the user. The user's browser now creates the necessary HTTP messages in IP packets addressed to 186.78.25.13, which are routed into the Internet via router A.